Hi everyone. We will go further with the chapter electric charges and fields. So in the last class we have already seen about the introduction of the chapter. So that means we have seen about the nature of the charge, how are they arranged in an entity. So very basic concepts we have seen. Today's class we will go with the next concept, that is properties of charges, and then we will see about the Coulomb's law. First we will go with the properties of charges. Next we will see about the Coulomb's law, which is very important, and under this we have equation, then vector representation of the form, direction, all those things. Then we will consider how to deal with the multiple charges. So first we will go on with the properties of charges. This is where very easy, but you have to remember all the properties so that all the concepts are used in the numericals. So first thing is charges. Under the charges, if we have positive negative charges or positive charges, how are they dealt? So like charges, most of you might be knowing this one. Like charges will always repel each other, and unlike charges will always attract each other. So that means if I have positive plus 5 Coulomb plus 5 Coulomb, they will always repel. Minus 5 Coulomb minus 5 Coulomb will also repel. So they will move in the opposite direction. Plus 5 Coulomb minus 5 Coulomb will always attract each other. So this is the basic example I have taken. Positive, negative, positive and negative. So what happens here? Like charges will always repel and unlike charges will always attract each other. And so this is the first property of charges. Second property is, it is also simple, additivity nature of charges. That means how you add the whole numbers or the natural numbers. In the same way we add the charges present in the system so that we get the total charge present in the whole entity. Suppose I have plus Q1 Coulomb plus Q2 Coulomb minus Q3 Coulomb minus Q4 Coulomb plus Q5 Coulomb. So how do you add this one, or how do you, if you are asked to find the total charge present in the system, then you just simply add plus Q1 plus Q2 minus Q3 minus Q4 plus Q5. So this gives the total charge present in the system, which I can represent as plus Q. You have to consider this minus sign also because it might be electron. So if it is electron, you have to consider the sign. So that means signs are taken into consideration. For example, if I have plus 5 Coulomb minus 3 Coulomb plus 1 Coulomb minus 2 minus 8 Coulomb. What is the total charge present in the system? So this is just you add plus 5 minus 3 plus 1 minus 2 minus 8. So 5 minus 3, 2, 2 plus 1, 3, 3 minus 2, 1, 1 minus 8 minus 7 Coulomb. So this is the total charge present in the system. What do you mean by Coulomb? Coulomb is the SI unit of charge. This you have already studied in your 10th standard. How will you define this Coulomb? I have I is equal to Q by T. What is I? Current. Q is charge. T is time. So you can define current as rate of flow of charges. So whenever the term T comes in the denominator, we tell it as rate of change or something. So you have velocity, rate of change of displacement. In the same way, you have rate of flow of charges is represented as current, I. So I, ampere, SI unit, Q as Coulomb, T as seconds. How can you define 1 Coulomb? If there is a flow of 1 ampere of current for 1 second, then the total number of charge present in that wire, if you consider, is 1 Coulomb. So if this is 1 ampere, this is 1 second, then this is 1 Coulomb. So this is the additivity nature. So first one is like charges, unlike charges, what happens over there. Second one is additivity nature. Next, third one is charge conservation. So that means we in our lower classes we have already studied that energy can neither be created nor be destroyed. In the same way, charges can neither be created nor be destroyed. Charge conservation. You cannot create any charge, you cannot destroy any charge, but you can transfer a charge from one system to another system. Okay, so you cannot create or destroy, but you can transfer. We have already studied in how you can transfer the charge through conduction. If you bring the two bodies, bring the uncharged body near the charged body, some of the charges get distributed to the other body. So in the same way, charge conservation. You cannot create or destroy the charges, but as a whole, the charge will always remain the same even if it is distributed to the another system. But in the nature also you have like this. If you have a neutron, it gets disintegrated into proton and electron. So before disintegration, total number of charges 0. After disintegration, total number of charges also 0, because you have proton and electron. So if I consider neutron, it disintegrates as proton plus electron. So the neutron is neutral, it is considered. So proton and electron is also as 0. So total charge is 0 after disintegration and it is 0 before disintegration. So that is what the charge conservation is. Okay. Next one is quantization of charges. Charge quantization. Q is equal to plus or minus n, where A is the charge of the electron. If you consider electron, you will get minus sign. If you consider proton, you will get as plus. So Q is equal to plus or minus n into E. What is this n? N is the number of charges, total number of charges which you add or give to the system or which you remove from the system. So this is Q is equal to plus or minus n into E. Suppose I have any charged body, say that it has a total charge of Q. Okay, this is a charged body plus Q I will tell. Bring one uncharged body near it. Uncharged body. What happens? Say that charges are distributed. So this will get Q plus Q by 2. This will get plus Q by 2. Okay. Now keep these two aside. Bring one more uncharged body near this one. What will happen? It gets divided again. Q by 4, Q by 4 like that. So you can divide the charges like this. Okay. But when you consider the whole system, the total charge will remain the same. It goes along with the charge conservation. No extra charge will not come into picture. So you can divide the charges or you can add the charges. Extra charges will not come. How can I add the charges? As n into E. Plus or minus n into E. In that way you can add the charges. Now for our consideration here in this chapter, also in further concepts which we consider as point charges. Point charges. What are these point charges? There is nothing difference between these. So point charges are nothing but if you have two charges like this, if their separation is very large when compared to the size of this one, then we consider it as point charge, a small charge. Okay. So we are always dealing with the point charges in our discussion. This one as well as in the next chapter, we consider the point charges in the discussion. So these are about the properties of charges. Now if I have very smaller charge, we go with the smaller units. So it might be millicoulomb or microcoulomb. Milli means 10 to the power minus 3 coulomb. In a system, if we have very minute charge, then we go with the smaller units, smaller SI units called as millicoulomb and microcoulomb. So it is 10 to the power minus 3. As you know, micro is 10 to the power minus 6 coulomb. Next is, under this quantization, we have continuous distribution. Continuous distribution of charges. Now what are these what is this continuous distribution of charges? Suppose I have large number of dotted lines, closely spaced dotted lines, very closely spaced dotted lines. If you see these dotted lines from very far, you see that as a straight line. Okay? In the same way, the micro distribution of charges, if you add very smaller charges to a system, you find that you cannot measure that very smaller units. As a whole system, you see that you have a continuous distribution of charges. So this is one small similarity which we can use. Dotted lines which you see from very far, you see it as a continuous charge, continuous straight line. So in the same way, you have the continuous distribution of charges. So adding a very smaller units, you cannot measure it like that, but as a whole, you can see that there is a large number of distribution of charges which is taking place in a system. So this is about the properties of charges. Next, we will go with the Coulomb's law. This law deals with the charges and their separation between the two charges. So as I have already mentioned, Coulomb's law, we deal with the point charges. So their size is very small. Coulomb's law. It tells us about the force experienced between 2 point charges and how are within their separation. If I have two charges Q1 and Q2 and if their separation is R, say that I have two charges here Q1, Q2, those two are separated by a distance R. Then it is found that force experienced by these two charges is found to be directly proportional to product of charges and inversely proportional to square of the distance between them. So if F is directly proportional to Q1, Q2 by R square, where Q1, Q2 are charges which are measured in terms of Coulomb and R is distance which we usually measure in meters in SI units. So I have already told, when we deal any concept, we deal with the SI units. So Q1, Q2 in Coulomb and R in meter. So it is found like this, Q1, Q2 by R square. Now, in order to remove this proportionality constant, I mentioned K, which is proportionality constant, K, Q1, Q2 by R square. This is very important. This is the force experienced by, very important, K, Q1, Q2 by R square. Okay. Now what is this value of K? This you can, for the numerical, you have to remember this value. For the numericals, K, value of K is actually 1 by 4 pi epsilon naught. Epsilon naught is the absolute permittivity of free space. So one more thing you have to keep in mind is we always consider it in free space or vacuum, this value. Otherwise this is not holding good. The value which we get, that is not proper. But if I consider K as 1 by 4 pi epsilon naught, where epsilon naught is the absolute permittivity of free space, that is in vacuum, and which we discuss in chapter 5 or 6. Okay, in that we have different terms. There you will get to know. So this value is found to be 9 into 10 to the power 9 Newton meter square per Coulomb square. This value you have to remember. For the numerical, this value you can write it directly as 9 into 10 to the power 9. Then Q1, Q2 values and R values will be given. Okay. So you are asked to find out the force. That is the simplest numerical which you get. So F is equal to 9 into 10 to the power 9. So this equation will become now F is equal to 9 into 10 to the power 9 into Q1, Q2 by R square. So this is also another form of Coulomb's law, which gives about the force experienced by the two charges. 9 into 10 to the power 9 Newton meter square per Coulomb square. What is the SI unit of force? It is Newton. So Newton, Coulomb, Coulomb, and this you have as meter square. So 9 to 10 to the power 9 Newton meter square. This Coulomb and Coulomb will come to the denominator. So you have per Coulomb square. So this is about the Coulomb's law. Okay. I hope it is clear. Next we will move on to the vector notation of Coulomb's law. This is also very important. Vector form of Coulomb's law. In order to represent this Coulomb's law in vector form, you have to know about the unit vectors. This you will study in grade 11 physics concept under vectors. Okay, this comes under laws of motion or motion in a plane. Under motion in a plane chapter, first you have these vectors. So in that you have different definitions. So many definitions you have already studied. Under that you have unit vector. What do you mean by unit vector? How will you represent? We represent it as cap. If I tell that I have n unit vector as n cap will give you a unit vector. Or if I have a vector a cap, how will you get that? Vector a divided by magnitude. So in the coming further, we will see next class, we will go with the further concepts regarding the vector notation, under that the multiple charges, how to deal with the multiple charges. Thank you.